Okay, we are now recording. Okay, now I'm going to share my screen. Now that the folder's copied over. Go back to fourth period. Click on materials. Okay. We are starting a new grading period. We're in the fifth 6 weeks. Okay. Today is March the 22nd, and it is a Monday. Okay. Now, guys, before spring break, we talked about universal gravitation before spring break. On today, we're going to review a little bit of universal gravitation, and then as soon as we get done with that, I'm going to get started on circular motion. Circular motion. So that's the goal for today. And as soon as we get done going over circular motion and working out a few example problems involving centripetal acceleration, then I'm going to let you guys go so you guys can do the assignment. It's basically 12 multiple choice questions. So I want to begin by reviewing what we talked about last time. So before the break, I showed you guys what is known as the inverse square law. And the inverse square law looks something like this. It basically says that the force of gravity acting between any two objects is equal to the gravitational constant big G times the mass of the first object times the mass of the second object divided by the distance between the two objects squared. Okay. So remember we talked about this equation before spring break. And remember I said that what this equation says that if you have any two masses, so let's say we have any two masses, what this equation tells us is that if you take those two masses and place them next to each other, there's going to be a gravitational force of attraction between those two masses. And I have two magnets to demonstrate this, but pretend these are just ordinary masses, and pretend the magnetic force is similar to the gravitational force. What the universal inverse square law says that if you take those two objects and you bring them closer to each other, the force of attraction is strong. If those objects are far apart, the force of attraction is weak. So there's an attractive force between those two objects. Okay. And this equation here basically allows us to quantify this force. And remember, guys, anytime we have variables in our numerator, that means that those variables are directly proportional to the resultant. What that means is, as mass increases, force of gravity increases. As mass decreases, force of gravity decreases. But what about any variables in our denominator? Remember, any variables in our denominator, they are inversely proportional to the resultant. So what this means is that as distance decreases, force increases. As distance increases, force decreases. As distance decreases, force decreases. Okay, that's what it means when we say two variables are inversely proportional. Okay, so and like I said, we went over that before the break. There's also something else that I want to go over with you all. If y'all remember, before the break, I gave you guys a paragraph length response. I want to pull that up and go over a few of these concepts with you guys right now. So, we'll just pull this up now. As soon as this file gets done converting, we can go over the main points. Okay, so if you guys remember last time, you guys worked on this paragraph length response, and this paragraph length response had a part A and a part B. Part A, a lot of you guys did good on part A. As I was reading your responses, a lot of you guys were spot on in part A. However, part B was a little bit more challenging. In fact, nobody got part B right. And, in fact, that was kind of surprised me. I did expect at least one person to get it right. But that was a pretty challenging question. Part B was pretty challenging, and it required some it required very, very deep thought. Because no one got this one right, I didn't count this against anyone because it was a really tough question. Basically, if you attempted to do part B, I gave you credit for part B. But part A, I thought part A was a very reasonable question. I had several students to get this right. But let's go ahead and look over part A and part B. And again, I want to briefly review this before we get started with circular motion. And the reason I want to do that is because on this assignment that you guys will be working on today, there's going to be some concepts that will be over this material. Of course, it's an all multiple choice assignment, but you guys still need to know these concepts to be sure you get the right answer. Okay, so guys, let us start with part A. Okay. Part A says, earlier this year, we learned that all objects here on Earth accelerate at a rate of 9.8 meters per second squared in the absence of air resistance. However, this value is not a true constant. In other words, the rate of 9.8 meters per second squared is only an approximate value for an object's acceleration that is falling downward to the Earth. Using the inverse square law, explain in your own words why the true acceleration for an object changes over time while the object is in free fall. Okay, now, so guys, imagine here that we have a red ball that is falling toward the Earth. And obviously it's falling toward the Earth because the Earth is pulling at it. Okay, there's clearly a gravitational force of attraction between the red ball and the Earth. So the Earth is pulling it downward, and this ball is accelerating toward the Earth. Now, guys, this rate of acceleration, even though at the beginning of the school year I told you guys that the acceleration of gravity is 9.8 meters per second squared, it turns out that value is only an approximate value. Okay? It's not an exact constant. Here's why it's not an exact constant. It's not an exact constant because of the inverse square law, right? The inverse square law says that as distance decreases, force should increase. So guys, think about this. As this ball gets closer and closer to the Earth, the distance between the ball and the Earth is decreasing. So that means the force of attraction must be getting stronger and stronger and stronger. Okay? So guys, if the force of attraction is getting stronger, that means that according to Newton's second law, then the acceleration must be increasing with that, right? Because a greater force causes a greater acceleration. So I'm gonna write that down. So as the ball gets closer to the Earth, the force becomes greater, which increases the object's acceleration. So that's basically the answer to this question. So the reason why the acceleration is not constant is because the force acting on it is not constant. Does that make sense, guys? How many of you guys felt confident about this one? When you guys answered it? Now, I know a good number of you guys got this right. So basically, guys, what this is saying is if I take an object and I drop it to the Earth, if I take the object and I drop it to the Earth, Stephanie, you should still be able to see the assignment and your grade. It's because you can go back to it. Yeah, you can see it. I mean, I didn't write anything on it. I just put your grade on it. Like if you got a 100, then you got this question right. If you got some points taken off, then you probably likely missed this question. It was called I can't remember, what was it? Universal gravitation, inverse square law, something like that. But anyway, but guys, here's the point here, guys. So when the ball is up high, its acceleration, it may be around like 9.7 meters per second squared. Okay. As the ball falls and gets closer to the Earth, because the force gets stronger, that acceleration picks up. So at some point, it might be somewhere around 9.73 meters per second squared. Okay. If it keeps falling, it might be somewhere around 9.8 meters per second squared. Okay. And it gets closer and closer to the Earth, it might be somewhere around 9.82 meters per second squared. Okay. So guys, here's the point. The point is, okay, the point is that this acceleration actually gets greater and greater and greater as the object descends toward the Earth, because the force acting on it gets greater over time. So the point is 9.8 meters per second squared is an approximation for the object's acceleration. It's not a true constant. It's an approximate constant, but it's not a true constant for this reason. Okay. Any questions on part A? So that explains why is it that the object's acceleration changes over time while the object is in free fall. Does that make sense, everyone? Stephanie, guys, does this make sense? All right. Thank you, Angelina. Thank you, Stephanie. Thank you all for responding. Thank you, James. Okay, now part B. This was the one. Thanks, Jerry. This was the one that a lot of you guys struggled with. Well, all of you guys struggled with this one, but it was a tough question. It really made you think. But let me explain this answer real quickly, just to be sure everybody understands what's going on here. Part B says, imagine a hypothetical situation in which an alien is flying above the surface of the Earth in a spaceship, as shown in the picture below. When the spaceship is 900 kilometers above a certain point on the surface of the Earth, the alien stops and decides to release a package to humans on the ground. In a clear, coherent, paragraph-length response that may also contain equations, explain why is it that the package does not travel with an exact distance of 900 kilometers before it collides with the Earth's surface. Okay, so let's look at this, guys. So imagine that this spaceship is above this point here, and it just stops. Okay, so the spaceship stops, and as it stops, it releases this package here. So the spaceship is releasing this package here that I kind of drew in black. Okay, now why is it that the package, as it falls to the Earth, does not travel the entire 900 kilometers? If there's exactly 900 kilometers between the spaceship and the Earth. Okay, here's why, guys. Believe it or not, the reason why is because of Newton's third law. Because of Newton's third law. Think about this for a second, guys. I want you guys to think very deeply about this. Okay. According to Newton's third law, the Earth pulls on the package, right? So the Earth is pulling on the package. However, remember, for every action, there's an equal and opposite reaction. If the Earth pulls on the package, then the package is also doing what? Pulling on the Earth. Okay. So guess what, guys? Not only is the package moving, but the Earth is also moving too. The Earth is moving toward the package. In fact, if the surface of the Earth is somewhere around here, by the time this package comes in contact with the Earth might have moved up just a little bit to where its new surface is somewhere around here. So its new surface may be somewhere around here. Okay. So the point is, by the time this package hits the Earth, it's not going to travel the full 900 kilometers, but it's going to travel a distance that's somewhat less than that. It may travel this distance here. So the actual distance, I don't know, I'm just going to throw out a number. It may be somewhere around 895 kilometers. instead of 900. Okay. And the reason why is because of Newton's third law. Because of Newton's third law, because the Earth is moving toward the package at the exact same time that the package is moving toward the Earth, basically that distance is going to be shortened. So by the time this package comes in contact with the Earth, the actual distance, instead of it being 900 kilometers, is going to be from around 890 something. Does that make sense, everyone? Guys, do you want to explain it again? I know that was kind of a Stephanie, it doesn't make sense? It does make sense? Okay.
Explain it again.
Okay, I'm explaining it one more time. And this time so Jeremiah, the basic idea, the answer involves Newton's third law, Angelina. Um, uh, the answer involves Newton's third law. Because think about it, because Angelina, many people don't realize this, but if the Earth is pulling on objects, objects are also pulling on the Earth. That's because of Newton's third law. Newton's third law always hold. Now I will say this though: the Earth is not going to travel as far upward. Um, no, it's not gonna travel as far upward because obviously the Earth is a much bigger mass than the package. So the package is going to have a huge displacement, but the Earth is going to have a tiny displacement. In fact, I'm actually exaggerating it here, but it's going to have a very tiny displacement because it's such a huge mass, right? Because even though the forces acting on both of them are the same, since the Earth is a lot bigger than the package, its acceleration is going to be much smaller, therefore leading to a much smaller displacement. Um, Angelina, it's okay. You're not the only one. No one out of all of my students, no one correctly got this right. No one answered this correctly. And I kind of expected it because I knew it was going to be a tough question. I knew it was going to really make you guys think. But that's the purpose. That's the purpose of these AP questions. These AP questions are to really make you think about the physics. Jeremiah, let me explain it again. Why is it that? And this time, let me hold on, let me delete this. Okay, so Jeremiah, you do understand that this package here is falling toward the Earth because gravity is pulling at it, right?
Yeah.
Now, Jeremiah, if the Earth was not moving, this package would travel a full 900 kilometers before it touches the surface. Okay, so you got that, right?
Yeah.
However, what does Newton's third law says, Jeremiah? Newton's third law says if the Earth pulls on the package also does what?
Does it accelerate?
It pulls on the Earth, right? So guess what, Jeremiah? If the package is pulling on the Earth is also moving. So the Earth moves toward the package.
Huh?
I know it's weird, right? But yeah, the Earth moves toward the package. Yes, right. So initially the surface of the Earth is right here. Okay, but because because the package pulls on the Earth is going to move just a little bit. So it's going to move upward, and this new surface is going to be somewhere around here. So the point is, Jeremiah, by the time this package comes in contact with the Earth, it's not going to travel the full 900 kilometers, right? So, the distance from here to here is the full 900 kilometers. It's going to only travel a fraction of that distance. In fact, the distance is going to be less than 900 kilometers. Does that make sense? That's because the Earth is moving too. I know that's weird. Wait. Yeah, huh?
Oh, so it's real. Like that's what actually happened.
That actually happens. Yeah. Now, let me be clear though. Even though the Earth is moving, I've kind of exaggerated the effect here. The Earth doesn't move this much. In fact, the Earth moves a very tiny amount, very, 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 very tiny amount. But the point is, it moves just a little bit, such that the actual displacement won't be 900 kilometers. It'll be less than 900 kilometers.
But don't things drop from the Earth like a bunch of times? I mean,
Yeah,
don't a
yeah.
lot
They
of things
all.
drop from the
Hey,
Earth?
guess what, Jeremiah? They all impact the Earth.
Are
You
you
didn't know that,
serious?
did you? Yeah. So right now, like you might not believe it, but right now, you see this object. You know, right now, as I'm throwing up this object, I'm literally shaking the Earth. Even if it's just a little bit, even if it's just a tiny amount, I'm shaking the earth by throwing up this object, right? Because of Newton's third law, right? When I throw up this object, the earth pulls on the object, but Newton's third law says the object also pulls back on the earth. So
So what
yes,
about rain?
everything impacts the earth. In fact, I don't know if you remember a few years ago, well, this was like maybe like a decade ago, when that earth, I think that when that earthquake happened in Japan, like the earthquake was so significant that it literally tilted the earth from its axis just a little bit. Because yes, for every action, there's an equal and opposite reaction. If things are happening here on Earth so violently, it can literally, cause the Earth to displace from its particular um, location. But yeah, everything
Uh,
impacts the Earth. Um,
the dinosaurs.
Stephanie, I still gave you credit if you answered that question wrong. Now I didn't give people credit for answering part A wrong because you guys should have got that one right. But I did give you credit for answering it wrong. If you attempted something, I still gave you credit, Stephanie, because it was such a hard question. But again, I have to give you guys hard questions every now and then because that's the nature of the AP exam. The AP exam involves hard questions. Okay. So everybody good there? Can I move on now?
Yeah,
Okay. Now, let us go to Schoology. Okay. Okay. Today we are going to start on circular motion. Circular motion. So I've included some notes in Schoology for you guys. Okay. And we're gonna get started going over these notes today, and then we're gonna finish them up on Wednesday. Okay, but let's just talk about this first page right here. So circular motion. Now, okay, guys, anytime you have an object that is moving in a circle, okay, its motion can be described by two things. Um, you can describe its motion by its centripetal acceleration, and you can also describe its motion by its tangential velocity. Okay, so what do these terms mean? Let's start with the first term. Well, no, you know what? Let's start with this term right here, tangential velocity. Let's start with explaining what this term is right here. Tangential velocity just basically means how fast an object moves around the circumference of a circle. Okay, so um, here's what I mean by that. Let me just show you guys a visual of what I mean. Okay. Okay. So guys, here we have an object here moving on a circle, and it could be any object. It could be Earth. It could be the Earth going around the sun, or any sort of object moving in a circle. These same principles hold. Okay. Again, anytime we have objects moving around, going around a circle, okay, we can describe its motion using two terms. We can describe its motion by its tangential velocity and also by its centripetal acceleration. What is tangential velocity is? It just refers to how fast the object is moving around the circumference. Okay, let me okay, let me show you guys what that looks like. Okay, okay. So guys, look at this circle here. You guys see this arrow here in purple? That arrow in purple shows us our object's tangential velocity. Okay, uh, so this arrow, it's a vector. and it's showing us tangential velocity. And guys, remember what a vector shows us. Vector shows us two things. A vector shows us magnitude and direction. So basically, guys, what this arrow here is telling me, um, um, it's telling me, one, how fast the object is moving at that point. So the length of the arrow represents how fast it's moving, and the direction the arrow is pointed in shows us where the object is going at that point. Okay, so that's what a tangential velocity vector is. A tangential velocity vector shows us the magnitude of the velocity and its direction. Okay. The important thing that I need for you guys to know is that all objects moving in a circle, every object moving in a circle, has a tangential velocity. Okay. So, and just to be clear, guys, I want everyone in here to understand what precisely this arrow is telling me. Okay. Uh, like, like if I had to give a real world example, what is this arrow telling me? Well, guys, imagine that this was the Earth here going around the sun. So imagine that the sun is right here at the center of this circle. So it's obvious that the Earth is keeping, I'm sorry, it's obvious that the sun is keeping the Earth in orbit. Okay. Let me ask you guys a question. Imagine for a second that I could turn gravity off. So imagine this moment right here. I decide to just turn gravity off. Oh, hold on, let me pause it. Why is this not? Question, guys. If I turn off gravity right at this exact moment in time that the Earth is going around the sun, what's going to happen to the Earth right at that moment? Do you guys
It's
think?
gonna float away from.
Well, let me ask you a question. Well, is it going to keep going in an orbit? Is it going to spiral inward to the sun, or is it going to float away in a straight line? What do you think?
It's gonna go into the sun.
No, it won't. It will not.
But isn't
I think
so
you were right the
so
first time.
so it's gonna float away.
It's going to float away, but it's going to. But is it going to float? Is it going to float away in a curve, or is it going to keep traveling along a straight line?
It's probably gonna follow the arrow. Maybe I don't know.
Uh, okay, I heard Jeremiah's answer. What do y'all think? Do y'all think it's going to? It would it would go outward in a curve or to follow a straight line? Ooh, Angelina says a curve. Okay, so let's see. Um, Actually, Angelina, it turns out Jeremiah is right on this one. It's going to follow a straight line. Here's why: because Angelina, what does Newton's first law says? If there are no forces acting on an object in motion does what? An object in motion,
It keeps going.
yeah, it stays in motion, right? There's no. Now remember, we turn gravity off. So if we turn gravity off, it's going to keep going in a straight line, right? It's at a constant velocity. Um, to be specific, guys, if I was to turn off gravity right at this point right here, then guess what the object is going to keep doing? The object, it turns out, is going to keep going straight like this. Okay. It's going to follow the arrow. In other words, it's going to follow the direction of the tangential velocity. Okay. So hopefully that gives you guys an idea of what the tangential velocity is telling us. Guys, what about this situation right here? Question: What if, um, what if I decide to turn off gravity while the object is right here? What's going to happen then? Then in this case right here, then the object is going to follow that line there, and it's going to spin off in that direction. In fact, it's going to eventually leave the solar system, right? Because in the absence of gravity, in the absence of a force, is going to keep going along a straight line. Same thing if I turn it off here. If I turn it off here, then the object is going to follow this line right here. It's going to follow that straight line right there. Does that make sense, guys? But yes, Angelina, yes, it's going to follow in a straight line because of Newton's first law. Yep. Right, because remember what I said, I turned off gravity. There's no force to keep it in orbit. So as long as there's no force keeping it in orbit, it's going to keep going in a straight line. So that's what I mean when I talk about tangential velocity. Okay. Guys, any object that's moving in a circle has a tangential velocity. And basically, we can visualize the tangential velocity by using a velocity vector. Remember, a vector tells us two things. It tells us magnitude and direction. The length of the arrow tells us how fast the object is moving. And the direction is pointed tells us its direction of travel at that precise point. Okay, so that's what we mean when we say tangential velocity. Okay, now let's talk about centripetal acceleration. Okay. Guys, any object moving in a circle has also what is known as a centripetal acceleration. And the centripetal acceleration here is what is represented by the blue arrow. Okay, the centripetal acceleration of the object was represented by the blue arrow. Okay. So let me write this down because this is an important term that I want to write down here. Okay. Guys, anytime you all see that term centripetal, guess what centripetal means? Centripetal literally means center seeking. Center seeking. Centripetal means center seeking. So, going back to our video, and here's a basic fact that I need for you guys to know, that anytime you have an object moving in a circle, that object has an acceleration that is always pointed inward. It's always pointed toward the center. Okay, that is always true. Okay, so let me go back to this video here. So remember, in purple here, the arrow in purple shows us our tangential velocity vector. And then this arrow in blue shows us our centripetal acceleration vector. Okay, so it shows us where the object is accelerating. It's always accelerating toward the center. Okay. And guys, I want y'all to think logically why that is. Okay, guys, think about this for a second. Anytime an object that is moving in a circle, it is always true that the force that is acting on that object is always pointed toward the center. Always true. That's why we say that the acceleration vector always points toward the center, right? Because force is what causes acceleration. And guys, I want to prove this to you all. And here's how I'm going to prove this to you guys. I'm going to show you guys another clip that's going to prove to you guys that for any object moving in a circle, the force acting on that object is always pointed toward the center. Look at this video clip right here that I'm about to put on. Okay, let me go ahead and share my screen again. Okay, guys, in this video clip right here, I want you guys to look closely at the bowling ball. Okay, notice how in the video, in order for the bowling ball to move in a circle, notice what the guy holding the broom has to do. So look closely. Guys, tell me, in that video, in order for the bowling ball to maintain its circular path, the force from the broom has to always be pointed where? What do you guys notice? Where is that broom pointed?
In front of it.
Well, but the force is pointed where? The force acting on the bowling ball, where is it pointed?
Towards the logo.
Yeah, in other words, toward the center of the circle. Can everybody see that? I'm gonna rewind it a little bit. So notice, okay, notice how in order for the bowling ball to keep moving in a circle, notice how he has to keep pushing the broom inward. In other words, the force from the broom is constantly being pushed towards the center. Can everybody see that? Does that make sense?
Good to us.
Guys, that is always true for any object moving along a circular path. That is always true. Always. In fact, notice when there's not a force acting on it, the ball is traveling in a straight line. But the moment the boy starts pushing on the broom toward the center, notice that's when the bowling ball starts moving in a circle. Okay. So guys, as a basic rule, in order for an object to move in a circle, the force acting on it must be pointed toward the center. In fact, the force is what causes it to have a centripetal acceleration. Any questions there? Does that make sense? Let me show you guys one more example. Who in here has ever seen people do donuts in a car? Okay. Or any of you guys ever done donuts yourself?
No.
No.
Some of us are young.
Me. Angelina, you sound like you've done donuts yourself. Stephanie says she's seen it. Well, guys, in this video clip right here that I'm about to show, so look at these people doing donuts. So look at these two cars doing donuts. Notice they're continuously moving in a circle. Guys, in order to do donuts, there's only one way you can do a donut. It turns out that the frictional force between the tires in the road, you have to orient your tires in such a way so that the frictional force always points toward the center of the circle. If the frictional force isn't pointed toward the center of the circle, the car can't do a donut. So, in other words, anytime the car is doing a donut, it must have a centripetal acceleration. So it must have a centripetal acceleration. In this case, the frictional force from the tires is what's causing the object to have a centripetal acceleration. Okay. So everybody got that? Okay. So yeah, Jeremiah, the police is right there with them. I'm pretty sure they were just having a little fun. But anyway, guys. Oh, by the way, don't you guys try that because that's very dangerous. But I just want to sum up everything that I said before we do the math problems. Because I'm gonna close out the day just doing 3 math problems with you guys. So, guys, just to sum up everything that I just said.
Not that difficult. The brief overview in this video should help to understand the topic.
Okay, let me open up this video clip here. Okay, guys, to sum up everything that I just said, anytime you have an object moving in a circle, its motion can be described by 2 variables. It can be described by a tangential velocity and it can be described by a centripetal acceleration. Okay, so So let's start with the arrow, the vector that describes its tangential velocity. Okay, so the tangential velocity vector, um, um, the reason why we call it a tangential velocity is because it shows us two things. It shows us how fast the object is moving at that point, and it shows us where the object is traveling at that point. Okay. We can also describe the object by its centripetal acceleration. Um, the centripetal acceleration vector basically tells us the direction of the force acting on the object, right? Because the force is what's causing the object to accelerate toward the center. Okay, so if you guys got those two things down, you guys understand the concepts. Now, the last thing that I want to write down for you guys today, I want to write down the equation for centripetal acceleration because you guys are going to need this equation whenever you guys are working on the assignment. So here's the equation you guys are going to be using for your assignment. Okay. Guys, an object's centripetal acceleration is equal to the object's tangential velocity squared divided by the radius of the circle. Okay. So this is the equation you guys are going to use to do your assignment. So AC here means centripetal acceleration. And I'm just going to write down what these terms means. Okay. VT stands for tangential velocity. And again, tangential velocity just refers to how fast the object is moving around that circumference. And guys, in this equation right here, R means radius. It represents the radius of the circle. Now, this equation right here, R does mean radius. I know in the equation I gave you guys last time here, R meant distance. But in this equation right here, R does mean radius. Okay. So if I were you guys, I would write this down or take a screenshot of this so that you guys will have this equation next to you all whenever you guys are working on your homework assignment. Okay. So anytime an object is moving in a circle, it has a centripetal acceleration. And that centripetal acceleration is mathematically equal to the tangential velocity squared divided by the radius of the circle. Okay. Now, with that said, guys, what I want to do, I want to do about 3 examples with you guys from this PDF file right here that says centripetal acceleration practice problems or practice examples. So let's just do that, and then I'm gonna let you guys go.
Wait, so you said the assignment today is multiple choice?
Yep, it's multiple choice.
So it's a test.
I'm sorry?
So it's like a test. It's not a PDF.
Yeah, it's not a PDF file.
Okay.
But I do want to work out some mathematical examples for you so that you would know how to do them on the assignment. And I'm gonna work out a few of these examples from this PDF file that I have posted. Okay. All right, guys. I'm just gonna do about a few of these, maybe like 3 of them with you all, just so you guys can get the point of how to work this equation. Okay, look at number 4 here. Let's start with number 4. Number 4 says a water wheel built in Hamas, Syria has a radius of 20 meters. If the tangential velocity at the wheel's edge is 7.85 meters per second, what is the centripetal acceleration of the wheel? Okay, so let me open up another blank sheet of paper so I can do number 4. Okay. So looking at number 4. Okay. All right, so guys, notice we're given 2 things. We're given the radius of the wheel is 20 meters. we're also given this tangential velocity, as we told us, 7.85 meters per second squared. So we can easily calculate the centripetal acceleration. The centripetal acceleration is equal to tangential velocity squared divided by the radius. So I'm going to write that down. Okay. So centripetal acceleration is equal to the tangential velocity squared divided by the radius. Okay. So guys, let's just plug everything in on number 4. Notice it said that our wheel has a velocity of 7.85 meters per second. Okay. So I'm going to plug in 7.85 into this equation. Remember, that gets squared. Okay. All of that divided by the radius. What does it say? On number 4, the radius of the wheel is 20 meters. So the radius of the wheel is 20 meters. Okay, so now, guys, all you have to do is put this in your calculator, and then this will tell you the centripetal acceleration of the wheel. So 7.85 squared divided by 20 is equal to 3.08 meters per second squared, right? Acceleration is always meters per second squared. Okay. So that's how you do number 4. Any questions on how to use this equation?
Are all the questions like going to be like this?
I'm gonna work out 2 more examples. Some of the questions will be like this. Some of them will be slightly different. Just depends on what it asks you. But I'm gonna work out 2 more examples just so you know how to do all the problems. Yes, Angelina, this is the official number. That is the official number, 3.081125. Yeah, thank you for doing that calculation with me. Okay, guys, let us do 2 more examples. I want to do enough of these examples to where you guys will know how to do the assignment. You know what? Let us start with number 1. Well, not start, but let us do number 1 next, and then after that, I'm going to close out the day doing number 3. So I'm going to do number 1, number 3. Number 1 says the largest salami in the world is made in Norway and was more than 20 meters long. If a hungry mouse ran around the salami's circumference with a tangential speed of 0.17 meters per second, the centripetal acceleration of the mouse was 0.29 meters per second squared. What is the radius of the salami? Okay, so guys, they give us 2 things. They give us tangential speed, which by the way is just another word for tangential velocity. It's 0.17 meters per second, and they give us the centripetal acceleration, which is 0.29 meters per second squared, and they ask us to solve for the radius of the salami. Okay, so guys, going back to this equation here, you see the equation here? I want to take this equation and I want to solve for radius. In other words, if I was to get r by itself, that would look something like this. So if I was to get r by itself, r would be equal to the centripetal. I'm sorry. That's wrong. It's equal to the tangential velocity squared divided by the centripetal acceleration. Okay. So guys, if I take this equation right here, if I take that equation right there, rearrange it, and solve for radius, this is what I get: tangential velocity squared divided by centripetal acceleration. Okay. So now that we have our equation, let us go back to number 1. Okay. So guys, they tell us our tangential speed. Our tangential speed of the hungry mouse was 0.17 meters per second. Remember, tangential speed mathematically is the same thing as tangential velocity. So 0.17 meters per second. I'm going to plug that in for the tangential velocity. I'm going to square that. And then all of that gets divided by the centripetal acceleration. Okay, guys, what is the centripetal acceleration of the mouse? It tells us it's 0.29 meters per second squared. So I'm going to plug in 0.29, okay, into this equation. So now, what is the radius here? Put this in our calculator. Okay. Angelina, I know you did the math here. Is this what you got, Angelina, when you did it? 0.9. So, something close to that? All right. Awesome. Awesome. Yeah. And again, since radius is a unit of length, our units are going to be in meters. 0.099655 meters. Okay. By the way, if y'all want to write this equation down, I will go ahead and do that now. Basically, all I did was just if I take this equation right here, rearrange it, and solve for r, I get that. Okay. Now, let us do one more question, then I'm going to let you guys go. One more question. Okay. Look at number 3. Number 3 says, an ostrich lays the largest bird egg. A typical diameter for an ostrich egg at its widest point is 12 centimeters. Suppose an egg of this size rolls down a slope that has the centripetal acceleration of the shell at its widest point of 0.28 meters per second squared. What is the tangential speed of that part of the shell? Okay, so in other words, it's asking us to solve for tangential velocity. Okay, so guys, for number 3, what I need to do, I need to take this equation right here, I need to rearrange it, and I need to solve for tangential velocity. So when I do that, this is what I get. When I rearrange that equation to solve for tangential velocity, I basically get the centripetal acceleration times the radius, and then take the square root of that, and that gives me my tangential velocity. Okay. So this is the equation we're going to use to do number 3. Okay. Again, all I did was just take this equation right here, rearrange it, and got tangential velocity by itself, and this is what I get when I get that. Okay. So now, going back to number 3. Okay. Okay. So guys, we know. Okay. So guys, we know that in order to solve for tangential speed, or in other words, solve for tangential velocity, we need to know the radius, and we also need to know the centripetal acceleration. Guys, let us figure out what the radius is. Guys, notice what this says here. It says the diameter of an ostrich egg is 12 centimeters. 12 centimeters, that's exactly equivalent to 0.12 meters. Okay. So if the diameter of the ostrich egg is 0.12 meters, can someone tell me what is the radius of the ostrich egg? If we know its diameter, which is 0.12 meters, what is its radius? Anyone?
The radius is like half of that, or you multiply it by 2.
The diameter, the diameter, yeah, radius is half the diameter.
So it's 0.6.
Not 0.6, but 0.0, 0.06 meters. Yeah. So
yeah. That's what I meant. That's what I meant.
0.12 divided by 2 is 0.06 meters. Yeah, James, 0.06. Okay. So guys, if our radius is 0.06 meters and our acceleration is 0.28 meters per second squared, we can easily solve for the tangential velocity by plugging everything into this equation here. So let's do that now. So tangential velocity is equal to the square root. Okay. Remember the centripetal acceleration of the egg is 0.28. We just said the radius was 0.06. Okay. So guys, we're going to multiply those together and then take the square root of all of that. So take the square root of 0.28 times 0.6, and let's see what we get. 0.28. Angelina, what did you get? Okay.
Mr. Terry, do you mind like scrolling up just a little bit so I can see like the top equation?
There you
go. Oh, appreciate it.
Yeah, so do 0.28 times 0.06, and then take the square root of all of that, whatever that is. Yeah, Jerry, I got what Angelina and Stephanie got. I don't. How did you get 0.03? Yeah, Angelina and Stephanie, you're right. It's 0.1296. Of course, and remember, guys, since this velocity, the units are meters per second. Jerry, did you see what you got? Did you see where you went wrong? Okay. So, any questions on how to use this equation? And again,
So
guys,
pretty much.
I'm sorry.
So pretty much the questions are going to either ask for the acceleration, the velocity, or the radius.
Exactly. Yeah, the mathematical questions. Yeah.
And the three examples you did is how to solve all three of those.
Exactly. Exactly. Yes, sir.
All right.
You got it. Yeah, and there's guys, don't worry about working on the problems in the PDF file. I mean, you can if you want to, but you don't have to turn those in. The only thing you're going to turn in for today is this assignment right here. It's a multiple choice assignment, and it's called Gravitation and Circular Motion. Again, some of the concepts is going to come from the gravitational topic that we talked about before spring break, and then most of the concepts, though, on this assignment is going to come from everything that we talked about today. Okay. So to sum up what we talked about, anytime something is moving in a circle, its motion can be described by two things. It can be described by a centripetal acceleration vector, or it can be described by a tangential velocity vector. Okay. So if so guys, imagine this was the Earth going around the sun here. Okay. So guys, the Earth obviously moves around the sun. Why does the Earth move around the sun? Well, that's obvious. There's a gravitational force between the Earth and the sun. So the sun is pulling on the Earth. Okay, and guys, it should be obvious to you all the direction of the gravitational force, right? So the gravitational force acting on the Earth is always directed toward the center, right? It's always pointed toward the sun, right? So what we say is that the force that's causing this object to have a centripetal acceleration is always pointed toward the center. Um, and of course, the tangential velocity basically tells us two things. This arrow here tells us um, where this object is going, right? It's telling us direction, and it's also telling us how fast the object is moving at that point, right? So the length of the arrow refers to how fast, right? Because remember, vectors refer to magnitude and direction. Any questions? All right, let me go stop recording.